Servo systems need to be tuned, and tuning can be a real hassle. Fortunately, the SureServo 2 provides one of the best tuning algorithms in the industry, and most of the time, it'll be all you ever need. But if you need more control over the auto-tune process, the SureServo 2 system gives you several options. Tuning Mode 1 allows you to manually specify the frequency response level. Mode 2 also gives you control over the load inertia instead of letting auto-tune estimate it. And Mode 3 adds control over the command responsiveness. Of course, if you're some kind of servo savant, you can always manually tune a drive, but that means taking control of 3 or 4 dozen interrelated parameters yourself. Yeah, good luck with that. The point is, the SureServo 2 system lets you work at whatever level you're comfortable with. For this video, we'll stick with the auto-tune, which does an excellent job, and again, most of the time, it's all you'll ever need. I'm using the same hardware that we used in the quick start video, but I also added this 4.5 pound steel pulley to give us some inertia and shimmed its 5/8 bore down to the 14mm shaft size using a 3D printed cylindrical spacer. I reset the drive to factory default so you know exactly where I'm starting from. Now don't forget to do a power cycle after a factory reset. That ensures that any residual non-volatile parameters get cleared out. Auto-tune is completely self-contained, so you don't need to do anything to prepare for it. You can run auto-tune from the drive's keypad. The user manual shows you step-by-step how to do that, but it's much easier to use the free SureServo 2 Pro software in a USB cable. I'll connect to the drive and read the servo info so you can see what hardware I'm using. Click on auto-tune. Now you have two choices. You can have your controller control the motor's motion or have the drive do it. You would use the controller option if you have a servo in a system and a controller already driving it along the intended path. That way you can tune it to your exact application. I don't have a controller connected, so we'll let the drive control the motor during auto-tune. The software warns us to make sure the emergency brake works, no one's near the machine, and it warns us that the system may resonate and do some funny stuff, so don't be alarmed. And if you have a braking motor, make sure the brake is not engaged. The software sees I haven't turned the motor on yet. I can do that via my panel switch or just do it here. I prefer to do it here because then I don't have to remember to turn the panel switch off when I'm done. And again, the software warns us to make sure everything and everyone are safe. Yep. Now I need to tell it how fast to spin and how fast the ramp should be. You want to emulate what your system will be doing. Now it's important to make sure the speed is fast enough to get a good bump when the motor changes directions so auto-tune can get a good feel for the inertia it has to deal with. A jog speed of 20 RPM is way too low to do that. That's only 1/3 of a rotation per second. So I'll put that at 1000 RPM for our little spinning pulley demo. Likewise, to get a good bump when the motor changes directions, we need the ramp times to be reasonably fast. So I'll leave those at 200 milliseconds. If you can do faster, then make sure this is as small as is realistic for your system. Again, you want to simulate the kind of jerking around your system will be giving the motor as best you can. If you'll be using S-curve in your application and you know what the value is, then add that here. We'll skip that for our demo to give us a good hard change in direction. We'll skip these for now. Just note that those are the same parameters the different modes we mentioned a moment ago give you control over when doing the semi-automatic tunings. Hit the download button to send all of this to the drive. Now we need to tell the drive how far the motor needs to go between direction changes. When we specify these two positions for the motor to bump back and forth between, they need to make sense. That is, if we start here at position 1, ramp up at this rate, run for a while, and ramp down to position 2, these positions, or this total duration, needs to be far enough apart to give the motor time to ramp up to speed. If you don't give it enough time, then it won't have time to ramp up to speed, and auto-tune will throw some errors at you and will shut down. So I'm going to take my current position and copy that to position 1 by clicking this button. Now by holding down these jog buttons, I can move my system to a new position that's far enough away that the motor has time to ramp up and back down. That makes more sense than a linear motion example, but for us, I'll just let it rotate a few revolutions. Okay, that ought to be enough time to get up to speed. Again, nothing precise here, just need to go far enough for it to ramp up to speed, or better yet, to match the system you'll be using it in. Just make sure you get at least one full revolution. Auto-tune won't work if you don't. Now I just copy that position to position 2 by hitting this button. And I can still modify these two parameters if I want to and download them to the drive. And again, we'll skip that. Everything is set up, so we hit the Start Moving button. Now this gives us a chance to see if we believe the system is getting up to speed and everything's working as expected. If not, then we would hit Stop, go back and modify things, and try again. Looks like this motor is getting up to speed, so I hit Next. And the software reminds us one more time to make sure everyone is safe. And auto-tune begins. Now if you watch these parameters, you can see it's taking less and less time for things to stabilize, and the overshoot is getting smaller and smaller as the tuning gets better and better. Looks like it found a harmonic resonant frequency and applied a notch filter to suppress the mechanical resonance the auto-tune found. Cool. And we're not getting any overload warnings. So far so good. You can also see how long it's taking up here. Looks like the motor current is around 260% of rated. That tells us we're trying to handle a large load. The max overshoot is in PUU. That's pulse user units. That's determined by the electronic gear ratio of parameters 1.044 and 45, which by default is 100,000 PUU per revolution. I'll fast forward the video a bit, and when these numbers get nice and small, auto-tune's done. When I hit OK, we see a list of all the parameters auto-tune optimized. This is the parameter number, what it was, what it is now, and a brief description. These are all of the parameters you would have to manage if you did this manually yourself. Yeah, now you see why I'm such a big fan of auto-tune. Parameter 1.37 tells us that auto-tune calculated roughly a 36 or 37 to 1 inertia ratio mismatch. It's crazy that the Shure Servo 2 system can handle that. Most servo systems need the mismatch to be lower, in the 3 to 1 or 5 to 1 or maybe even a 10 to 1 range. The reason the Shure Servo 2 can handle such a large mismatch is because it has a 3.1 kHz bandwidth, which makes it responsive enough that it can handle extreme inertial loads. Now don't miss this step. Auto-tune has calculated all of this for us, but they have not been written to the drive. I really wish this button was a lot bigger or highlighted or something because it's easy to miss. I'll hit Update, and now all of the new tuning parameters are in the drive. Now don't miss this step either. Make sure you read the drive parameters back into the Shure Servo 2 Pro workspace so when you save it to disk, you have a copy of the new auto-tuned parameters. Auto-tune returns the drive to whatever mode you were using, except you'll now find that the Shure Servo 2 system is more responsive and accurate. One of the really cool things you can do with the Shure Servo 2 Pro software is you can run the scope while auto-tune is doing its thing. In this example, I tracked the commanded position versus the actual encoder position. If we zoom in on the early data, we see the white is the commanded position, and the purple trace of the actual shaft position lags by about this much and misses the mark by about this much. If we zoom back out and then in on one of the ladder commands, we see the lag is only this now, and the tracking is much better. All courtesy of auto-tune and the built-in O-scope. Very cool. Just make sure you set the O-scope window width to something wide, use 32-bit numbers, and start the scope before you run auto-tune. You won't be able to run it once auto-tune started. There's a whole separate video teaching you all about the O-scope, so check that one out when you get a chance. If auto-tune has trouble completing due to the high inertial load, then try slowing down the jog speed and increasing the ramp times. That'll usually get things working. And of course, you can also adjust these guys. Also, if it's really struggling, it could be because you have too much inertia for the motor to drive. Check out this video on how to use the built-in inertia estimator. It's an awesome feature of the free Shure Servo 2 Pro software that figures out the inertia of the system for you. Well, that ought to be enough to get you started with auto-tune. Meanwhile, click here to learn more about the Shure Servo 2 system and to find more tutorial videos like this one. Click here to subscribe to our YouTube channel so you'll be notified when we publish more videos like this, and click here to learn about Automation Direct's free award-winning support options.